talking about wellbore stability and trying to understand how we can predict when the rock is going to fail around a wellbore. Basically, what we saw Monday was that whenever we have a wellbore, stresses change around the wellbore, and that change of stresses may cause failure around the wellbore. Sometimes shear failure, sometimes tensile failure. And that's what we want to predict right now. In order to see and to calculate what is the variation of that stress given external loadings, we said that we're going to use the Kirsch equation solution. And that Kirsch equation solution is going to allow us to predict those stresses based on some equations that depend on stresses, on pore pressure, and also the well pressure. You have a question? Yes, sir.
Did you start the recording?
I did. Yes, you didn't see that? Pretty sure I did. Let's see. Yes. Yeah, okay, I see the bar for the microphone, so that should be fine. Okay, so the first step was to understand cylindrical coordinates. And the most important thing to remember here is what is radial stress and what is hoop stress. The radial stress is a stress which is in direction of the radius, and the hoop stress is the one perpendicular to that one on the plane perpendicular to the axis of the wellbore. So now if we look at the wellbore from the top, we are going to be able to see what are going to be the stresses around this wellbore when we add different types of loadings. So, yes?
Could you explain again what sigma infinity is?
Yes, I'm going to explain that now. I'm actually going to put all the possible loadings before we solve them. So, I started with sigma infinity, but sigma infinity is just one component of what we can have in a wellbore. If we have a wellbore, and I'm looking at the cross section, and here is a wellbore, always we have far field stresses. And let's imagine that this is a vertical wellbore for now. Let me ask you the following, something that you should know by now very well. Are the horizontal stresses always the same in different directions? No, right? Why? Because sometimes there are tectonic stresses that cause the stress to be different in different directions. So let's imagine in this case that in addition to this background far field stress, I have higher stress in this direction. So now we have what is called an anisotropic state of stress. The stress in this direction is greater than in this direction. Inside the wellbore also we're going to have fluids. And those fluids are going to apply a pressure inside the wellbore that is going to depend on a few things that we're going to discuss in a little bit, but it's going to be an internal pressure inside the wellbore, like similar to what you would have in a pipe. In a pipe, when you pressurize it, you have a pipe inside in the cavity. And the last thing to take into account here is that this is going to be a rock, and therefore inside the rock we're going to have pores, and those pores are going to have also a fluid pressure. That paints now the complete picture of what we have in a wellbore. Anisotropic state of stress, pressure inside the wellbore, and also pressure in the pores. Well, in order to make this easier and to understand all the variables involved in here, what we're going to do is we're going to call the far field stresses sigma infinity, where sigma infinity is the stress in this direction and is equal to the stress that's going up and down. Because we have an anisotropic state of stress, we're going to add some stress, which we call it delta sigma, meaning that there is an additional stress in this direction, up and down, that in this direction. And inside the wellbore, we're going to have a pressure, which we're going to call it PW, W from wellbore. And inside the rock, as we know, we have fluids, and we're going to have a pore pressure. The combination of all of those are going to allow us to see and to solve all the stresses in the wellbore. And in order to make it easier, what I'm going to do is to break this apart in all these components. And the first one that we saw, it was what would be the effect of just a far field isotropic stress sigma infinity. So this is going to be sigma infinity, plus we're going to see later what is the effect of having an internal pressure PW, plus what is the effect of having a stress just in one direction, and later what is the effect of having a combined pore pressure inside the rock and a mud pressure inside the wellbore. So we're going to see all of those separately. And we already saw the first one, right? The first one, it's an application of a far field stress. Even if it's the same in all directions, we saw that when you get to the wall of the wellbore, and remember in this case we're considering that there is no pressure inside the wellbore. One, the radial stress is going to be 0 all around the wellbore, and second, the hoop stress is going to amplify 2 times when you get to the wall of the wellbore. So that means that whenever you get in this direction, wherever you are, there's going to be a compression stress circumferential around the wellbore that's going to be 2 times what you had in the far field. And the last thing that we said, that because of that, having a radial stress equal to 0 at the wall of the wellbore and a hoop stress which is not 0, the only way to have such thing stable would be that your rock has some finite unconfined compression strength. So even though if your minimum principal stress sigma 3 is equal to 0, still your wellbore can resist a compression in the other direction, which is lower than the unconfined compression strength. So that's why you can make wellbores in rock, and they are stable even if there is no fluid inside. We were saying that if you were to try to do this in a unconsolidated sediment, like sand, like dry sand, this is not going to work, because if you don't have radial stress, you don't have effective support on one direction, and you cannot put any stress on the other direction. So this is an unconsolidated sediment, this is a cemented rock. Okay, so let's move now to the next one. So we did this one, and we see that by putting a wellbore, stresses change, and now we need a cemented rock in order to support the wellbore. What about putting pressure in the wellbore? What do you think is going to happen when we put pressure inside the wellbore, and that's it. That's nothing else. No far field stress, no diatoric stress, no nothing. What is it going to be the hoop stress and the radial stress in such case? So now we just have pressure all around the wellbore. Is the same. It's applied by the fluid. My question is, here at the wall of the wellbore, what is going to be the hoop stress and what is going to be the radial stress? Let's go with the easy one. What about radial stress? What is going to be the value of radial stress? PW. Why? Because it's applied radially, and in order to be in equilibrium, you are applying to the rock a pressure, and we're assuming now that there is no porosity, no permeability, no nothing. So if you apply a pressure on it, the radial stress is just going to be PW. So if this is again theta, and this is sigma, here we're going to have, let me see the colors I was using last time. Sigma RR is going to be PW, and what do you think about sigma theta theta? Don't tell me the value, but tell me, do you think it's going to be a compression or a tension? That's the only stress being applied. Is a wellbore going to get bigger or smaller as you apply pressure? Bigger, and therefore, what do you think in radial direction? Is the wellbore going to be stretched or is it going to be compressed? In this direction. If it had a size like, say, like this, once you apply pressure, it's going to get a little bit larger, and so it's going to be stretched in this other direction. So while the radial stress is going to be a compression, is going to be positive, now applying a pressure is going to result in tension in the wall of the wellbore. And again, this is pi, and this is 2 pi. And it's going to be the same in all directions. Very similarly to what we had before for the far field stress, the equations are not going to change much, and probably I will skip writing the equations now, but you can find them in here, okay? So this was the first example, and this is now the second example, in which we have a pressure, and now this is a stretch in this direction but compressed in the radial direction, and the equation is very similar to what we saw before. And also the effects of stresses decrease very quickly as you get further away from the wellbore. So it's similar to the other one, but with different magnitudes of stresses. Any question about this one? Yes?
I'm still confused. Why is it stretched? Why is the direction of the sigma theta goes outwards?
Instead of thinking about here a rectangle or a cube, probably you could think about this as a pipe, right? If you're pressurizing a pipe with an inner pressure PW, when you pressurize it, the pipe is going to get a little bit larger, right? And in order to counteract this pressure, around the pipe, you need tensile stresses that keep the pipe together. And it's very similar in this case. It's just that those stresses, they decrease with distance as you get further away. So when you get very close to the wellbore, you feel a lot the influence of the inner pressure, but as you go further away, you don't feel it anymore. And remember that here we're considering solely the effect of inner pressure and nothing else, okay? All right, so this is this one, and now let's go and talk about this case. That case is similar to the first thing that we did when discussing wellbore stability. And usually when you talk about differences in horizontal stress in the subsurface, that goes by something called differential stress. And we're going to see that that differential stress is also very important, not only for wellbore stability, but also for hydraulic fracturing. Okay, so what is going to be, in this case, the radial stress? On the wall of the wellbore. Let's do it on the wall of the wellbore. And there is no fluid inside. There is nothing inside. It's going to be 0, right? And what do you think is going to be the hoop stress? Is it going to be the same as you go around the wellbore with an angle theta? Let's look only at the wall of the wellbore. At this location, when theta is equal to 0, what would you expect? Compression, tension, or a 0 value? What do you think?
Compression.
Here, compression, right? Because we're pushing in this direction, and therefore the stress have to go around the wellbore and will amplify. The compression will amplify in here. So very likely at 0, this stress is going to be a compression. Let me change something that, so I keep it the same as in the notes. Actually, let's put these stresses. It's the same thing, okay? It's just a definition of theta, just to be consistent. Let's put it sideways. So what you just said now is the same as saying that at theta equal to 90 or at theta equal to 270, we're going to have a compression. And that compression is going to be a value over here, and also is going to be a value over here. And before we put everything, for theta equal to 0, would you expect to have a compression or a tension or 0 value? What? Well, it's not that easy to say, okay? And now, but that's why we need the Kirsch equation. But the Kirsch equation tells you that if you just had this differential stress on this direction and no other stress in the other direction and no pressure inside the wellbore, at this location over here and there, you will have a tension. So here and here, you will have a tension, And the value of that tension is actually the value of the differential stress, and the value of the compression on the other side is 3 times the differential stress. And last, the value of let me see, which one was sigma r? Sigma theta theta, it actually varies as a harmonic function, and this is going to be sigma theta theta. Remember, this is at the wall of the wellbore, and as we said before, this is going to be sigma RR equal to 0. Yes.
How did you get 3 times that?
Well, that comes out of the Kirsch equation. It wasn't something that we showed in class, but if you solve the Kirsch equations, we're going to write them, but not really write them, but I'm going to show you the equations in a bit. You will see that if you plug the right values for just having a differential stress, that would be 3 times. But the important thing here to remember is that if you remember before, we said that whenever we had an isotropic loading, we could amplify stress 2 times. Well, now if we have an anisotropic loading with stress just in one direction, sigma theta theta divided sigma, in this case a differential stress, at the wall of the wellbore, and at theta equal to, that would be pi over 2, 90 degrees, is equal to 3 times. So now the stress gets amplified 3 times instead of 2 times, because we have stress just in one direction. Similarly to the case before, we may run into locations in which we have a lot of compression stress and no stress in the other direction, and we could go into shear. So very likely these are the points where you may expect shear failure. While notice that there are some other points around the wellbore that you may expect, if you surpass the value of the tensile strength, to have a tensile fracture. Yeah?
So wouldn't one of the assumptions for the Kirsch equations that the rock has to be isotropic?
Yes, that was the assumption for the equations we're showing here.
Would that be, does that mean isotropic loading or just isotropic?
No, isotropic properties, material properties. But the state of stress is not the same in all directions. Okay, yeah?
Was this determined experimentally, like with the value like 3 times greater?
That's something that you're going to do in the laboratory. You're going to see how close you get to what the equations from Kirsch tell you. And if you have a very nice isotropic homogeneous materials, you'll get very close to this. And but with rocks, it's sometimes a little bit different. All right, so we need one more thing. So, yes?
Sorry, can you explain again why is it that you have compression or tension at a different angle?
So, let's concentrate on, let's imagine that we are a piece of rock around the wellbore, okay? And let's say that we are here at theta equal to 0. That will be this point. Here you're going to have tension because your stresses travel like this. The compression stresses bend, and at that point they depart in different directions, and so you end up with a component of tension in this direction. That's that point. As you move towards that point, it's that point over there. Now your stresses travel in this direction, and then they all accumulate at that point, and that's why you have your compressions to be higher. And then as you move here, you arrive to the same point as the one that is 180 degrees apart, and then you arrive there, and that's the same point, and then you come back to the same position which you started off. And this is exactly the same to what we were discussing when we did this example. But now this one is with a little bit more of detail. Yeah. Yeah.
So if you added delta sigma, like on top and bottom,
Yeah.
you get 2 times again, right? Because it would cancel out, the tension would cancel out.
It will depend on the relative magnitude of delta sigma compared to sigma infinity.
Okay.
So now you know it's an equation that you have to solve. But we're going to do that with some examples, okay? All right, so let's see now the final one. The final one was taking into account, we did this one, taking into account the effects of wellbore pressure, but also pore pressure. Okay, so this one probably is the one that it's the most difficult one to sometimes to understand, and also is the one that is going to vary also in the wellbore, and it's not going to be always the same. So let's say that we have a wellbore, and let's say that we have pressure in the wellbore because we have drilling mud in there, but also we have pore pressure inside the pores of the rock. Now let's make a zoom out of this at the wall of the wellbore, and I'm going to look at that in a large. Here is going to be the pressure of the wellbore, and now here is going to be the rock, and I'm going to assume, let's say, that we have a sandstone. Okay, tell me, what is drilling mud made of? Let's assume a water-based drilling mud. Water and what is mud? Clay. Clay. What else? Salt. Clay is bentonite too, right? And sometimes you can add some other materials in it in addition to clay. But basically, it's a mud because there is clay, and let's say this is a sandstone with a grain size of 100 microns. Is clay bigger or smaller than 100 microns? A lot smaller, right? Well, sometimes in addition to clay, you may put some other materials so that when you are drilling against the wall of the wellbore, you have fine particles that accumulate, and they do not, most of them, they do not get into the rock. Sometimes you may get a few particles in there because this is not perfect, right? But the idea is to make a layer of a very low permeability that can maintain a difference between the pressure in the wellbore and the pore pressure in the formation. What is the name of this?
Mudcake.
It's a mudcake, right? It's a mudcake or a filter cake, and in order to be effective, you need to design that. Well, let's plot what would be the profile of pore pressure as you go from the wellbore to the rock. First of all, is your wellbore pressure going to be smaller or larger than your pore pressure? The wellbore pressure. Pore pressure, wellbore pressure, most times you want it to be larger than the pore pressure. Otherwise, fluids are going to get into the formation. We're going to get into those details later on. Probably you already saw some of that in drilling, but most times you want to get a pressure in the wellbore which is higher than the pore pressure. What the mudcake does is it enables a transition zone from a high pressure in the wellbore to the pore pressure in the formation. So this difference is what really the rock feels. And that difference is what is really applied on the wall of the wellbore. What forces make possible this stress? Well, before answering that, the mudcake, which is going to be located here, is going to be very similar to the membranes that you have been using in the laboratory. The membrane has a very low permeability, almost zero, right? And you put the fluid on one side and no fluid on the other side, and the fluid doesn't go through, and that's what allows you to apply a stress on the rock. Where on the wellbore is very similar, but now you don't have a latex membrane or a heat shrink membrane. Now you have another type of sort of membrane, but it's made of the mudcake. And as the fluids try to go into here, they drag those particles, and that dragging applies a stress on the wall of the wellbore. And what is the nature of those forces? Friction, right? This is a viscous fluid, and as it tries to get in, it pushes the grains into the rock. I don't know if you guys have ever done skydiving, or there you get to feel the forces of friction, even if it's just air, right? I remember once I was in a mountain skiing, and the wind was so strong that I would just throw myself back, and the wind would just hold me there on my entire weight. It was very, very windy that day. So these forces can be very strong, and those are actually that add an effective stress to the wellbore and add wellbore support. And that, as we're going to see, that's going to be very important for wellbore stability. Okay, so now let's put everything together. And the result of putting, I didn't write the equations, okay, but the equations for the differential stress are these ones, and the variation is sinusoidal, and here you see there is a cosine and there is a sine. Once you put all the stresses together, these are the equations that you get, in which we have the effect of the pressure on the wellbore, or effective stress on the wellbore. We have the effect of the far field stress, and notice that here is just an average of the stresses perpendicular to the wellbore, on the plane perpendicular to the wellbore. Notice the negative sign. This is the differential stress, and here you have normal stresses, radial stress, hoop stress, and also the shear stress, and this is the axial stress, that is just a combination of the other two with a Poisson ratio. So when you put all of that together, you are going to be able to tell what are the stresses everywhere around the wellbore, close to the wellbore and far from the wellbore and at any angle. And in this example, we have a stress in this direction, which is 12 megapascal, stress in this direction, which is 3 megapascal, and no support or no stress on the wellbore wall. And as a result of that, what you get is radial stresses that vary depending on where you are, hoop stresses that also vary depending where you are. And notice that here the warmer values mean more compression, and because the larger stress is going sideways, you have more compression at these locations, and you even have a little bit of tension. Notice that value is 0, so there is tension at those points. And that's what the Kirsch solution gives you. In the homework, you're going to have to do a similar problem, but I'm not asking you to plot these colorful field stresses. I'm just asking you to tell me what is the stress at a given angle. Say, for example, if you have theta equal to 0, I'm just asking you the stresses along this line. Or if you have theta equal to 90, I'm asking you the stresses along that line. Okay? If you feel like doing this, you're welcome to, but that's not necessary or mandatory. But with the Kirsch equations now, you can tell exactly what are those stresses around the well. Okay, so, but we care about these stresses because we want to say whether the rock is going to fail or not. And in order to do that, we need to go one more step. And instead of computing just the normal stresses, as you know, when we get further from the wellbore, we also have shear stresses. You can also compute the principal stresses. In this case, this one is sigma 1, and this one is sigma 3, and shows you that the maximum stress, compression stress, again is at this location, and the minimum compression stress is at that location. Here you have tensile failure, here you have compression failure. Okay. Any question so far? Yes.
So when your maximum stress is horizontal, that means that your 0 point is like on that horizontal line. Is that correct? Is that angle
You refer to this one or to that one?
to the top one? Yeah. So
Yeah.
you said at 0 degrees, that's like the horizontal, correct?
0 degrees, that would be in this case here, yeah.
And that's based on the largest stress, like where it's being applied. Like the largest stress is horizontal.
Correct. So the stress coming in this direction, right? The largest one. There is also stress in that direction, but the largest one is coming in this direction. So the maximum compression is there, here and there.
But it does change. Like let's say the larger stress was vertical. That means would 0 be at the top now? Like the 0 degree mark would be at the top.
If you had the stress coming in this direction, up and down, your theta will start at that location. Theta, I already modified these notes, but I added a few comments saying that theta is always measured from the direction of SH max. So that's something to remember. That's very important. Okay? Okay, so let's do one more thing today, which is now that we know stresses all around the wellbore, the last thing to do is going to be to tell what the stresses are at the wall of the wellbore, and that's going to help us reduce the equations that we are using. Yes?
There's a quick question on example 2. I think you said that stresses decrease very quickly as you go away from
Yeah.
the wellbore.
Yeah.
Why is that for that example in particular?
It's actually for all of them.
Oh, okay.
So look at this again at this plot. You can see that there is a lot of compression near the wall of the wellbore, but as you get further away, we get to a value that shows like more or less like what, between 15 and 10 in this direction. So that hoop stress is actually 12.
Okay.
You go a little bit further away and you get 12. You get a little bit further away from here and you get to that blue color, which is more or less around here, and that's actually 3.
Okay. Yeah, I thought it was just for number 2. But that
No,
makes
no,
sense.
for all the examples, the stresses change, and kind of like the amplification, the change of stress dies away very, very close from the wellbore. Yes?
So the maximum horizontal stress was pointing in the vertical, then theta equals 0. Which
Yes.
is at the vertical
Yes,
axis.
correct. Yes.
And your wellbore would always fill in the opposite direction, right? The vertical.
The shear will be always located opposite to the direction of the maximum stress.
And then what about the compression?
Yes, these points. So these points are going to be always opposite to the direction of the maximum stress.
That is shear, not the compression.
This is shear.
Okay.
This is failure in shear. And we're going to see that later on, because actually this is very useful. Because sometimes you can see a wellbore and you can say, well, the shear failure is located, say, at 45 degrees from the north towards the east. And because of the orientation of that failure, you can say, oh, because the wellbore has failure at this angle, I know that the stresses probably are coming in this direction, because the wellbore is telling you that. The wellbore reveals the direction of the stresses if you have failure in them. Okay, so now we need to solve the Kirsch equations, but now we're going to do that at the wall of the wellbore. And in order to do that, in this long equation that you see that there is a variable r, we're going to replace the variable r by a. And when you replace r by a, notice that here, for example, this is just going to be 1. This is going to cancel out. This is going to be 1. This is going to become 2. And therefore, all of these complex terms and long terms are going to simplify. And eventually, you will get just to an equation for the radial stress, which is this one over here, in which the radial stress is just the effective stress support that you have due to the pressure in the wellbore minus the pore pressure, and the hoop stress is going to be just this equation, in which we still have a component that depends on the angle, the cosine of 2 theta. So here, what we are interested is on telling what is the stress at 2 specific locations. When theta is equal to 0, which will be a point over here, and where theta is equal to pi over 2, which will be a point over there. And when you do that, you will see that the Kirsch equation eventually simplifies a lot more, and you get that the hoop stress it's equal to this value over here whenever theta is equal to 0, and whenever theta is equal to pi over 2, it simplifies to this equation. Notice that sigma h max is going to be higher than sigma h min, right? So this value over here is going to be higher than that one over there. So always at pi over 2 or 3 pi over 2, you have more compression than at pi over 0 or pi equal to 180 degrees. So what we're going to do next class is we're going to use this equation, and we're going to combine what Kirsch tells us with what we already know of rock failure with tensile strength and with shear failure to see what are the limits of the stress and pressure inside the wellbore that allows us to predict when the wellbore is going to fail or not. Remember that there is no lab this week and it's going to be next week. All right? See you on Friday.